All right, get ready because today we're diving deep into emergence.
Oh, fascinating topic.
It is. It's where you have simple things interacting to create something entirely new and complex.
Yeah.
How single cells create a living organism, or how individual ants form a colony that acts as one.
Yeah.
But we're not going to just scratch the surface.
Okay.
We're going to explore emergence through a unique lens, triadic thinking.
That's right. And to do that, we need to introduce you to the ideas of a philosopher named C.S. Peirce.
C.S. Peirce.
Pronounced like Peirce.
Okay.
And Peirce was convinced that to truly grasp anything, we need to think about it in sets of three.
Sets of three.
Firstness, secondness, and thirdness.
Okay. I'm intrigued by this.
Yeah.
But at first glance, thinking in threes sounds a bit simple.
Yeah.
How does that help us understand something as complex as emergence?
It's deceptively simple.
Okay.
But that's where the power lies. Let's start with a concrete example.
Right.
Imagine a single biological cell.
Okay.
The cell itself, with all of its potential.
Yeah.
That's what Peirce would call firstness.
Firstness. So that's...
It just is.
It just is.
The potential.
Okay, so firstness is like the raw material, the potential for something to become.
Exactly.
What about secondness?
Secondness comes into play when that potential meets a constraint,
Okay.
a reaction, something distinct from itself.
Distinct, yeah.
In the case of our cell, that would be its DNA.
The DNA.
The DNA exists separate from the cell body,
Right.
but it provides the instructions, the blueprint for what that cell can become.
So firstness is the potential. Secondness is the blueprint that shapes that potential.
Yeah.
But where does the actual emergence happen? That's where thirdness comes in.
Exactly.
Okay.
Thirdness is that magic ingredient.
Okay.
It's the relationship between the first and the second, where something truly new and unexpected arises.
Okay.
In our cell example, thirdness is the incredible process by which the cell body, the information, encoded in its DNA.
Encoded in the DNA.
Using it to build and maintain itself.
So it's not just the cell body on its own, the firstness, or even the DNA as a separate blueprint, the secondness. It's the interaction between the two.
Exactly.
The interpretation and action that truly makes a cell. That's where the complexity emerges.
Precisely.
Wow.
And this principle goes way beyond biology.
Okay.
Echoes of this triadic interplay in all sorts of complex systems.
In all sorts of complex systems.
Take language, for example.
Okay, how does language fit into this triadic framework?
Think about it.
Okay.
Individual letters or sounds, on their own, they're just potential...
Pure firstness.
Pure firstness.
Got it.
But when we combine them into words, we introduce secondness.
Secondness.
A specific structure, a set of rules for how those sounds relate to each other.
So letters are firstness, words are secondness, and then I'm guessing sentences or even entire conversations are the thirdness.
Exactly.
That's where the meaning emerges.
Exactly.
Right.
The meaning of a sentence isn't just the sum of the individual words. It's something more, something new that emerges from the specific arrangement and interaction of those words in a particular context.
Wow. I'm starting to see how powerful this triadic thinking can be.
Yeah.
It's like a framework for understanding how complexity arises from simple building blocks. But you mentioned that this applies to all sorts of complex systems.
Yeah.
Can you give me another example?
Let's look at technology.
Okay.
Think about the development of computers. You start with simple electrical components like transistors, pure potential.
Pure firstness.
Pure firstness.
So the transistors are like the basic building block.
Then you have the logic gates,
Okay.
which combine those transistors in specific ways to perform simple operations.
Okay.
That's secondness.
Secondness. All right.
Imposing structure and rules on those basic elements.
Okay, I'm following you. So where does the thirdness, the emergence, come in with computers?
Think about what happens when you start combining those logic gates into more and more complex circuits.
Okay.
Suddenly you have a system that can perform incredibly intricate calculations, store information, and even run programs. That's the emergence of a whole new level of complexity.
So just like with the cell and its DNA, or words forming sentences, it's the relationship and interaction between the parts, guided by specific rules, that leads to something much greater than the sum of its parts. Starting to see a pattern here.
And that pattern is a key to understanding those jumps to universality.
Jumps to universality.
We see throughout history.
Can you remind me what those are again?
Think about the invention of written language.
Like,
Suddenly, we could encode an infinite number of ideas using a finite set of symbols or computers, where, as we discussed, you can build any logic you want, from simple gates or DNA, the code for all life on Earth.
Okay, that's definitely ringing a bell now.
Yeah.
But how does this tie back to triadic thinking and emergence?
If you look closely at these jumps, you'll notice they all involve systems built from reusable, combinable parts.
Reusable, combinable parts.
Take written language.
Okay.
We combine a limited set of letters to form words, then combine those words into sentences, paragraphs, entire books, conveying an endless variety of thoughts and ideas.
So it's like the more ways you can connect the pieces, the more possibilities there are for something totally new to pop up.
Yeah.
And we see that same principle in computers and DNA too.
Exactly.
Right.
That's the principle of modularity.
A modularity.
And it seems to be a driving force behind these jumps to universality.
Yeah.
Modularity allows systems to become increasingly complex and sophisticated without becoming unmanageably complicated.
Because instead of needing a completely new element for every new function, you can just rearrange and recombine the existing modules in new ways.
Exactly.
That's brilliant. But how does this all relate back to me, the listener?
Well,
why should I care about this seemingly abstract philosophical concept?
Because this framework gives you a powerful new lens for understanding complexity in any field.
Okay.
From the evolution of species, to the development of new technologies, to even understanding the creative process itself.
Creative process, wow.
Triadic thinking helps you see the world in a whole new light, to recognize the patterns and potential for emergence all around you.
Okay, I'm starting to see the light. But my brain is definitely feeling a bit full right now.
Sure.
Maybe we could take a pause here.
Of course, we've covered a lot of ground already.
Yeah.
But trust me, we're just getting started. So far, we've seen how Peirce's triadic thinking, this idea of firstness, secondness, and thirdness, helps us understand how complexity emerges from simple interactions.
Yeah.
And we've connected this to those jumps to universality, like language and computers, where modular systems suddenly unlock immense potential.
Right. It's like those systems found a secret recipe for emergence, combining simple elements in increasingly complex ways, guided by rules and relationships.
Exactly.
But I'm curious, is there more to this recipe?
Yeah.
What else contributes to those breakthrough moments?
That's a great question.
Yeah.
And it leads us to another fascinating aspect of Peirce's triadic model.
Okay.
He argued that there are also these in-between spaces.
In-between spaces?
The gray areas between the main three concepts. He called these degenerate concepts.
Degenerate concepts.
And they create a set of tensions that any system has to navigate.
Okay, degenerate concepts.
Yeah.
That sounds a bit intimidating.
Yeah.
Could you break that down for me? What are these tensions all about?
It's not as complicated as it sounds.
Okay.
Imagine a tug of war.
Okay.
On one side, you have a force pulling in one direction, and on the other side, an opposing force pulling in the opposite direction. That's essentially what these tensions are.
Yep.
Fundamental forces that push and pull on any system, shaping its evolution and potential for emergence.
Okay, I can picture that.
Yeah.
What are some of these tug-of-war tensions that systems have to deal with?
One of the most fundamental tensions is between generalization and specialization.
Generalization versus specialization.
Yeah.
I think I'm starting to see how that plays out in the real world.
Okay.
In biology,
a
species needs to be general enough to survive in a changing environment,
but also specialized enough to thrive in its particular niche.
Exactly.
Yeah.
If a species is too specialized, it might be incredibly efficient in its current environment, but any slight change could wipe it out.
Yeah, that makes sense.
On the other hand, if it's too generalized, it might be able to survive in a lot of different places, but it won't be particularly good at anything.
Yeah.
Finding the right balance between generalization and specialization is key for survival and adaptation.
That makes a lot of sense. And I bet this same tension plays out in other areas too.
Absolutely. Think about businesses.
Businesses, okay.
A company that's too specialized might dominate a niche market, but struggle to adapt when new technologies or consumer demands emerge. Conversely, a company that's too generalized might lack the focus and expertise to compete effectively.
So finding that sweet spot between being adaptable and being excellent
is crucial for success.
It is.
Okay. That generalization versus specialization tension definitely resonates.
Good.
What are some of the other tensions that Pierce identified?
Another crucial tension is between individuality and constraints.
So my desire to be unique and express myself versus the rules of society or the limitations of my own biology.
Precisely.
Wow.
Every individual, whether it's a single cell, a person, or even a company, has a drive to express its unique potential. But at the same time, it exists within a larger system, a network of relationships and rules that impose certain constraints.
Like a balancing act.
Yes.
Too much individuality. The system might descend into chaos. Too much constraint. And you stifle creativity and innovation.
Exactly. Think about how this plays out in the evolution of language. On the one hand, you have individuals constantly inventing new words and slang.
Pushing the boundaries of language. But there also needs to be a shared set of grammatical rules and a common vocabulary for communication to be effective. The tension between individual expression and shared constraints is what allows language to evolve and adapt over time.
That's fascinating.
So
we've got generalization versus specialization and individuality versus constraints. Is there a third tug of war in this triadic model of tensions?
There is.
Okay, what is it?
The third tension Pierce identified is between diversity and pattern.
Diversity versus pattern.
Yes.
I have a feeling this one is going to be particularly relevant to understanding complex systems.
You're absolutely right.
Okay.
Think about an ecosystem.
An ecosystem.
You need a diversity of species to ensure resilience and adaptability. Different species play different roles, contributing to the overall health and stability of the ecosystem.
But you also need patterns of interaction.
Patterns of interaction.
Like food webs and symbiotic relationships to keep things in balance.
So too much diversity without any underlying patterns could lead to chaos, while too much focus on rigid patterns could stifle innovation and adaptability.
Precisely. It's about finding that delicate balance between the richness of diversity and the organizing power of patterns. And this tension isn't just limited to nature. We see it in human societies.
A vibrant society needs diversity of thought, culture, and experience to thrive. But it also needs shared values and institutions to provide stability and cohesion.
Exactly. And what's amazing is that the ability of any system to adapt, to evolve, to thrive comes from balancing these three tensions. Generalization versus specialization. Individuality versus constraints. And diversity versus pattern.
So it's not just about parts and wholes relating to each other. It's about navigating these fundamental tensions that exist at every level of reality. It's like these tensions provide the fuel for emergence. Pushing systems to constantly adapt and innovate.
They do.
And those jumps to universality we talked about, they often represent moments when a system finds a particularly elegant way to balance these tensions.
Exactly.
Okay, I'm starting to see how all these pieces fit together now.
Good.
It's like we're building this incredible framework for understanding not just emergence, but the very nature of reality itself.
It is quite profound.
But before we get too carried away, I am curious about one thing. You mentioned earlier that these jumps to universality often involve modular systems built from reusable, combinable parts. But how do those modular systems actually manage to bridge the gap?
That's a great question.
Between the digital world of information and the analog world of physical reality.
Excellent question.
Yeah.
And that leads us to another fascinating concept.
Okay.
Code duality.
Code duality, all right.
Think about a biological cell again.
Okay, a biological cell.
It uses the digital code of DNA for memory and replication.
Those instructions encoded in the DNA are like the blueprint for building and maintaining the cell.
But to actually carry out those instructions to interact with the physical world, the cell relies on analog processes. Chemical reactions and physical forces.
So you have this digital code for information storage and an analog system for interacting with the environment.
Exactly.
It's like having the best of both worlds.
It is.
But wait, you're saying this isn't just a biological thing, right?
Not at all. Okay, think about a computer.
All right, computer.
It uses digital code for processing information, but it relies on analog components like transistors and circuits to physically carry out those computations.
This code duality,
yes,
this combination of digital and analog, allows systems to combine the precision and stability of digital information with the flexibility and adaptability of analog processes.
Exactly.
That's incredible.
It is.
But how does code duality relate to those jumps to universality?
Well, it seems like this code duality plays a crucial role in allowing those jumps to occur because it allows systems to become increasingly complex and sophisticated without losing their ability to adapt and interact with the real world.
Because it allows them to store and process information efficiently while still being able to respond to the messy, unpredictable nature of reality.
Precisely.
Wow.
And what's even more mind-blowing is that some scientists believe our brains might work in a similar way.
Our brains.
We might use digital processes for abstract thought and language, but rely on analog processes for perception, emotion, and intuition.
So that feeling of knowing something without being able to explain it logically, that could be our analog brain at work.
It's a fascinating possibility.
That's wild.
It is.
It is.
And it raises an important question. If we can understand how code duality works in these complex systems, could we use that knowledge to create artificial intelligence that's more flexible, adaptable, and ultimately more intelligent?
Now, that is a question I'd love to see answered.
It is a big one.
But I have a feeling there's more to this concept of code duality.
There is.
What else does this model help us understand?
Code duality is intricately linked to the idea of self-referentiality.
Self-referentiality.
Which we touched on earlier with the cell example.
That whole parts and whole informing each other thing.
Exactly. Living things from single cells to complex organisms are fundamentally self-referential systems.
Self-referential systems.
They exist for themselves, create themselves, and maintain themselves. They have a sense of self.
A sense of self.
Even if it's not conscious in the way we think about it.
It's like they have an internal model of themselves.
Yes.
That they use to guide their actions and interactions with the world.
Precisely.
Okay.
And that self-reference is made possible through code duality.
Through code duality.
The digital code provides a stable representation of the organism's self, while the analog system allows that self to interact with the world and adapt to changing conditions.
So it's like the digital code is the blueprint for the self, while the analog system is the construction crew.
Yes.
That brings that blueprint to life.
A great analogy.
But how does a system know how to interpret its own blueprint? How does a cell know what its DNA means? How does a computer know how to execute a line of code?
That's where things get really intriguing.
Okay.
To answer those questions, we need to delve into the realm of semiotics.
Semiotic.
The study of signs and symbols.
Signs and symbols.
Think about it this way.
Okay.
Those instructions encoded in DNA, or the lines of code in a computer program, they're just signs and symbols.
Signs and symbols. Okay.
They have no inherent meaning on their own.
So the meaning comes from the way those signs are interpreted by the system.
Exactly.
Okay.
It's the system's ability to interpret those signs, to give them meaning within its own internal context that allows it to function and evolve.
Okay.
A cell's internal machinery acts like a tiny interpreter, translating the DNA code into actions.
Okay.
A computer's processor decodes and executes the instruction encoded in its software.
It's like each system has its own internal language, its own way of understanding and responding to the symbols it encounters.
Precisely.
Okay.
And this ability to interpret signs and symbols is essential for emergence to occur.
Okay.
Without it, systems wouldn't be able to build upon themselves to create something truly new and complex.
So we've got triadic thinking, modularity, code duality, and now semiotics. All these interlocking pieces coming together to paint this incredibly rich picture of how emergence works.
It's quite a tapestry.
But I have to admit, we've been talking about a lot of abstract concepts.
Sure.
Can we bring this down to earth a bit?
Of course.
Yeah.
It's one thing to talk about these concepts in the abstract, but it's even more fascinating to see how they play out in concrete examples. Let's take the example of the evolution of life on Earth.
Okay. Evolution of life on Earth.
A process that's filled with emergent jumps, driven by the very principles we've been discussing.
Like the first single-celled organisms arising from the primordial soup.
Exactly.
Or the development of multicellular life.
Yes.
Those seem like pretty big leaps in complexity.
Absolutely.
Yeah.
Those were moments when the tension between individuality and constraint, between diversity and pattern, led to a whole new level of complexity.
Right.
And those emergent jumps were made possible through modularity and code duality.
So modularity, like the way cells can combine to form tissues, organs, and eventually entire organisms. And code duality.
Yes.
Like the way DNA provides the blueprint for life, while cellular processes carry out those instructions.
Exactly.
It all starts to click into place.
It doesn't it?
And if we look at the evolution of technology,
yeah,
we see the same principles at work.
We do.
The invention of the printing press, the development of the internet.
Yes.
These were major emergent leaps that transformed human society.
Absolutely.
Okay, yeah, I can definitely see that.
Yeah.
The printing press relied on modular components, like movable type and a printing mechanism. The internet relies on the digital code of data packets and the analog infrastructure of cables and routers.
Exactly.
It's like these technologies tapped into the same fundamental principles that drive biological evolution.
Precisely.
And both of those inventions involved a jump to universality, right?
They did.
The printing press made knowledge more accessible and widespread. The internet connected people and information on a global scale.
Exactly.
And that jump to universality was fueled by modularity,
yes,
code duality, and those triadic tensions that push systems to find creative solutions. I'm starting to see the world in a whole new light.
Good. I'm glad to hear it.
But this isn't just about understanding the past, right?
No, it's not.
These principles are still shaping the future of technology.
Think about the development of artificial intelligence.
Okay.
Particularly the kind of flexible, adaptable AI we've been hinting at.
So the kind that could potentially revolutionize everything.
Exactly.
From scientific discovery to art and music.
That kind of AI will likely rely heavily on modularity and code duality.
Modularity and code duality.
Okay, will need to be built from modular components that can be rearranged and combined in novel ways. And it will need to bridge the gap between digital information processing and the analog world of human interaction.
It's like we're trying to recreate the conditions that led to those incredible jumps to universality in the past. But this time, we're consciously designing them.
We are.
But all this talk about AI and technology raises a question for me.
Okay.
You've been emphasizing how understanding these principles of emergence can help us understand the past and the present.
Yes.
But what about the future? Where might all this lead?
That's a great question.
What are the implications of these ideas for me, the listener?
That's where things get truly exciting.
Okay.
And that's what we'll explore next.
Okay, my brain is officially in awe of the universe and its sneaky ways of creating complexity.
Yeah, it's amazing, isn't it?
But you just said things get really exciting when we look to the future. What did you mean by that?
Think about it this way.
Okay.
If the universe itself seems to be evolving towards increasing modularity and intelligence.
Modularity and intelligence.
Those key ingredients for emergence, just imagine the possibilities that opens up.
Could these principles of emergence apply to us? To human evolution?
Absolutely. Think about how human thought itself might be a form of modularity.
Okay.
We combine concepts, ideas, and experiences in novel ways to create new insights, new inventions, new art. As we understand these principles of emergence better, who knows what incredible leaps in human creativity and problem solving we might unlock.
So maybe we're not just passive observers of this evolutionary process.
Maybe not.
Maybe by understanding these principles, we can actively participate in shaping the future, pushing the boundaries of what's possible.
Exactly.
But that feels like a lot of responsibility.
It is. And that's why it's so important for you, the listener, to engage with these ideas, to start seeing the world through this lens of triadic thinking and emergence.
Triadic thinking and emergence.
Look for examples of these principles in your own field, in your own interactions. Even in your own thoughts.
Okay.
Because once you start seeing the world this way, you can't unsee it. It changes the way you approach everything.
So what you're saying is that understanding emergence isn't just an intellectual exercise. It's a way of empowering ourselves to become more creative, more adaptable, more capable of navigating a world that's becoming increasingly complex.
Exactly. And who knows?
Yeah.
Maybe you'll be the one to discover the next jump to universality.
Okay.
The next breakthrough that reshapes the world as we know it. The potential is there, waiting to be unlocked.
That's an incredibly inspiring thought to end on.
Good.
This deep dive has been a wild ride.
It has.
And I feel like I've gained a whole new perspective.
I'm glad.
On not just how the universe works, but my own place within it.
And remember, this is just the beginning. Keep exploring, keep questioning, keep pushing the boundaries of your own understanding. The universe is full of emergent possibilities.
Emergent possibilities.
It's waiting to be discovered.
That's right. And who knows what amazing emergent properties might arise from your own journey of discovery. Until next time, keep diving deep